Next report, Enzo Bonacci, physics unit of ATINER rates, please.
Thank you very much. So, I will talk about the isomorphic issues about the CTCs in quantum physics. I would like to thank the organizers of this conference, in particular the chairman, Professor Prishliak, for the program committee, and the administrative committee chairman, Professor Egorov. So, the main solution to the Pochinsky paradox are Novikov's self-consistent causal loops, referring to a reciprocity principle, we call it also RP in physics, where the past determines the future, as well as the future determines the past. The recent proposal of a quantum circuit formulation of the famous Wormhole billiard ball paradox has renovated the interest for closed time-like curves, CTCs, applied to elementary particles. We wish to enrich such discussion by focusing on an electron entering a time travel tunnel so that it can collide with its past self at low energy. We investigated the graph isomorphism, GI, of two alternative cases about the exiting particle. If it is still an electron, then the collision deflects the trajectory of the incoming particle just towards the tunnel entrance within a stable time loop. If it is a positron, that is an electron moving backwards in time, the interaction with the incoming electron is a process of pair production, which is reversed inside the tunnel as annihilation according to the RP. Our GI analysis raises open questions ranging from the role of a preferential error over time to the validity of the level inertia in chronology violations. So, 1990, the Pochinsky Paradox. It was suggested by Pochinsky, that is a very famous physicist, that a solid elastic spherical mass, called a billiard ball, could enter in one mouth of a wormhole and exit at an earlier time due to a time shift and collide to its past self, earlier self, so that it would be averted from entering the tunnel. And it is a paradox. But just 1 year later, it was suggested, well, let's recall better what it means. We can see a scheme. It is retrieved from Wikipedia that explains exactly the paradox. So you can see the ball, the billiard ball. When it goes outside, it collides with its past self and it does not enter in the tunnel. Just 1 year later, it was suggested a solution. When the ball exits, so it collides with its past self just and only in the way to adjust its trajectory towards the tunnel entrance. So let's go on. In 2007, I suggested the reciprocity principle, that is a sort of extension of the principle of self-consistency of Novikov, and it is characterized by logical symmetry and temporal reversibility. And it raises a certain interest. And it is, to sum up, it claims the interchangeability between the subject, cause, and direct object effect within a well-formulated proposition. Let's go on. Everybody knows the cause effect, so the causality principle. The cause always precedes the effect along the ordinary arrow of time. But we can also assume the reciprocity principle associated to a time loop. In a time loop, the cause precedes the effect, but the effect influences the cause. There is a reversibility, a time reversibility. This is called a time loop. So, what is our time travel tunnel? Nothing difficult. We are not going to explore the general relativity equations behind such structure. It is just a tunnel, static, toroidal, with an entrance. You can see it on the bottom, and an exit. You can see it on the top. The entering and exiting particles are supposed low in order to neglect relativistic effects and to avoid high energy quantum processes. Very easy time machine. So, what are we going to investigate? An electron enters the static wormhole at the instant t in. There are two possibilities. The particle leaves the wormhole as an electron at the past time t out that is inferior to t in. Electron-electron interaction, and we will show how through graph isomorphism we will reach T-channel and U-channel molar scattering. But if the particle leaves the wormhole as a positron, it should be at the same time out equal to time in, and we're going to have an electron-positron interaction at time t inferior to time out, and through graph isomorphism, we're going to show that it will lead to an S-channel bubble scattering. So just for people who are not accustomed to S, T, U variables, they are the Mandelstam variables. Very easy to understand. So when the XT particle is an electron, we apply the principle of self-consistencies. So PSC by Novikov, that is a particular case of the reciprocity principle in physics. According to such principle, the collision between the two electrons deflects the trajectory of the incoming particle just towards the tunnel entrance within a stable time loop. The graph isomorphism leads to the T-channel and U-channel Feynman diagrams, both associated with molar scattering. This is the situation, the physical situation. We're going to zoom on the precise situation. So linear older-younger electron collision. And we can go on. There is another possible situation that the electron that is leaving the wormhole is not colliding with its past self, but with another electron. So second matter-only scenario, we're going to zoom it, and both the situation leads to the same T-channel exchange diagram. It is a very easy graph isomorphism applied to physics. Are there other situations possible? Yes, there are. Let's go on. Third matter-only scenario, we can see the electron leaving the tunnel that has a crossed interaction with its past self, its earlier self. We are going to zoom it to watch it better. But there are also another possibility to cross such interaction. That is the fourth matter-only scenario. But the both of them, we will zoom it, the both of them will lead to the same graph, Feynman graph diagram. So the graph isomorphism has led us to the U-channel exchange diagram, very famous diagram, and very easy to understand diagram. The situation is not exhausted. We have to explore the exiting particle as a positron. If the outgoing particle is a positron, that is an electron going backwards in time, we are assuming the Feynman-Stuckelberg hypothesis, we apply directly the reciprocity principle. According to the RP, the interaction with the incoming electron is a process of pair production reversed inside the tunnel's annihilation, which directs the trajectories of the particles each towards a tunnel mouth. The graph as homomorphisms leads to the S-channel Feynman diagram associated with Baba scattering. We're going to explore it. So this is the Feynman-Stuckelberg interpretation. You can see the positron going backwards in time. And this is the physical scenario, matter-antimatter scenario. The positron exits the wormhole and collides, interacts with itself in the past, its earlier self when it was an electron. And it is a process perceived by us as a pair production. But what happens inside the tunnel? The only possible process is the opposite, so the annihilation of particles. Such physical situation can be schematized through the following graph. This is a very easy diagram, and through a very easy graph isomorphism, we will reach the S-channel exchange diagram, the final diagram, S-channel exchange diagram, electron-positron. So, conclusions. Time travel scenarios are usually solved through causal loops, long closed time-like curves, CTCs. We have a rich, long list of CTCs solutions proposed for famous Pochinsky paradox, also known as the wormhole billiard ball paradox. We have explored it through a graph isomorphism related to the self-interaction of an electron at low energy, leaving a static wormhole at the same time of entrance as a positron or before as an electron. Our GI study results in Feynman's exchange diagrams, space S, time T, and U channel at undergraduate value. We didn't touch any formula. And we have implicitly assumed that the incoming particle influences the outgoing particle and vice versa. It requires a paradigm shift in physics to accept that the past affects the future as well as the future affects the past. The last binary sentence, where subject and object are interchangeable, is an application of the wider principle of reciprocity for well-formulated propositions in physics. This talk can be viewed in educational terms as a first formula-free approach to quantum electrodynamics. 3 final open questions. Antimatter as unique solution. One of our solutions of the Pochinsky conundrum is based on the electron traveling backwards in time as a positron. What would happen if the only way to travel back in time was to be or to become antimatter? We should rule out scenarios where the particle leaving the tunnel is still an electron. So the solution A and B should be ruled out. It will remain just the solution C we have explored before. Second open question. We have implicitly referred to low inertia by assuming that the exiting particle leaves the wormhole at a certain time, as if the tunnel did not move. It keeps the spatial coordinates. What would happen if the inertia principle was not valid in chronology violating regions? The outgoing particle would appear in a different locality with respect to the tunnel entrance mouth, avoiding any interaction with its past self. So the paradox would not exist. Third open question. A new paradigm in physics. The ordinary causal chain representation of events is incomplete for stable time loops, whose description is supplied by pairs of reciprocal propositions. What would happen if everything had also a retro-causal explanation? It is more philosophy than physics, but it is a possible scenario, we should regard any physical phenomenon as a whole beyond our common logic of observers who experience the conventional arrow of time. These are the references, and those are the image credits. Thank you for your attention. You've been very kind. That's it.
Thank you.
Thank you.
Questions, comments?
May I ask the question?
Yes.
Thank you for the very interesting report. It's connected with physics, and it's more interesting because I'm also a physicist and with orientation on mathematics. My question is connected with the following. You have considered such interesting principles as causality, but we know that in physics, so-called conservation energy, значит, законы. Вот. And so your conclusions about such unusual S, T, and U channels of reactions may be inconsistent with known energy momentum conservation and so on. What can you say about these conservation
Yes.
principles?
Well, we can be sure that any conservation principle is saved because we are considering closed time-like curves. In closed time-like curves, there's no possibility to lose or gain energy from nothing, from we don't know other sources. If we would have explored open time-like curves, your question would have been a grounded and inescapable question. This is the reason why I have ruled out, I did not present open time-like curves. I presented only closed time-like curves. So that I'm sure, because we come back to the same point where we start without adding or losing anything, energy included.
Yes, I understood. But my question is also connected with the following: what type of trajectory do you consider? What type of metrics? Is it space-like or time-like, or what? What can you say about it?
Well, though we have to say something as assumption. The hormone has been studied in a very difficult way, very difficult by Pochinsky and his pupils. It was a sort of model where the space-time matrix is exactly the same of general relativity, exactly the same. And it is consistent with such a model. After the Pochinsky proposal, there have been several applications of such model to different branches of physics, for example, quantum physics. But we have to consider two strong further hypotheses. First, velocity, the velocities should be low because we did not consider further relativistic phenomenon. And above all, the energy should be low because we are considering easy phenomenon without easy interactions, without further production of particles. low energy processes, if it is the question. So low velocity and low energy. The metric is the ordinary space-time matrix for general relativity. I have to add some another precision, that is, this presentation is for undergraduate students, in particular pre-university students, because a very big problem for teachers at pre-university level is that the heavy mathematical formulas discourage pupils. So I've tried a graphic only, graph isomorphism only, so that it will be reachable, understandable also by pupils without a strong knowledge in mathematics.
Okay, thank you. Only one remark short. If you consider quantum mechanically processes, are they connected to delta E about constant Planck? So you can consider such processes. Yes.
Yes, it is a simplified treatment of the problem, very simplified, because we want to avoid the. I would have liked to cite an author that treated the same problem as I did in a more complex way, but I thought, no, there's no reason to treat it. If you want, we can also write in private, and I will cite it when I will refer to his work. So you will understand better the differences between my very easy work, easy to understand and easy also as hypothesis, and his complex work. Because your criticism is very similar to his work, very, very similar.
Okay, thank you.
Thank you. More question?
Excuse me, dear Enzo.
Yeah.
Can you give us your presentation?
Yes, yes. You can find it
Give
on.
us a through chat. Very interesting,
Okay.
interesting stuff.
If you find my name on ResearchGate, it is already uploaded there.
Oh, thank you very
ResearchGate.
much. Thank you very much.
You will find as my last work, my last published work. It is just today. It is already published, already uploaded as a presentation. And so Bonacci ResearchGate. And I will write to Tatiana the name of a person which raised the same exactly criticism to the possibility of closed time-like curves applied to quantum physics. Exactly the same criticism. But if we assume low energy and not very high velocity, we can escape it. We can escape such criticism.
Thank you.
Thank you.
That's all. Thank you very much.
Thank you. You've been very kind.